already know. If I have the equation 1/2 x plus 2/3 equals 1/4. Okay? We don't like the fractions, right? We should be able to subtract 2/3 from 1/4. I think we have that ability. But what are you going to, if I'm going to take the 2/3 and subtract it from 1/4, what do I need between 3 and 4? Common denominator, right? I need both those to be 12, right? And then the next thing I want to do is multiply everything by 2 to solve for x, right? Okay? Well, in the event of getting that and that to the same denominator, I'd have to multiply this by 4 and this by 3, right? But then, ultimately, I'm going to multiply everything by 2, correct? So really, 4 times 3 times 2 is 24, right? So what I could do is go through there and multiply every single thing by 24, and that would give me 12x, 16, and 6 there, right? Okay, did I do that right? It'd be 8. Okay. Is that a little bit easier to solve than that first rational equation? All right. Now I multiplied by numbers that are a little bit too big because that's divisible by 2, that's divisible by 2, that's divisible by 2, right? So I could have just multiplied everything by 12 and it's fine. Okay. But we multiply by a common denominator to get all fractions to disappear, correct? Okay. Now you've been taught LCD, least common denominator. Okay. Basically, what can I make? And this is the question we ask when we want to find the least common denominator. What can I multiply to make that number, and that number all grow to the same value? The smallest same value. Does that make sense? Okay. And that smallest same value is 12. Okay. When we look at something like this, understand that the x and the x minus 3 and the 1, that is with the 2 as a denominator, and with the 0 as a denominator, those are all numerical values, right? When I know what x is. Does that make sense? When I know what x is, those are all numerical values. They might be 2 and -1 and 1 and 1. They might be 5, 2, 1, and 1. I don't know. Okay? Once I know what x is, those are all numbers. Well, in order to add those together, don't I need a common denominator with all those? Okay? So here's what we do is we try to figure out what's the least common denominator. And this one is not too bad. This is something we want to talk about because we're see these things pop up all the time throughout the year. Because generally speaking, when we want to take our math and apply it to the real world, in the real world, things don't come out to be real nice, cute numbers, right? They end up being fractional. They end up being, in this form here, which isn't that all that convenient. And really, if things in the real world came out to be that simple, we'd be really lucky. Okay. But it seems to be that the more complex the math is, it seems that it's more applicable to real world stuff. So we're going to see things that are a lot more complex than this, but we're going to do the same type of things. If I want to start adding and subtracting these things, I need a common denominator. Okay? So we go through and we try to find that. Now with variable expressions, it's going to be beneficial for you to find the least common denominator. Okay? In choosing the least common denominator, basically you go through all the denominators and you say, okay, if this term is new, I have to include it. Okay? So I go through this, and x obviously is the first one I come across, so it's a new term, so I have to include it as my common denominator. X minus 3 is new, so I include it. 1 is new, but that's just times 1, so we're fine. Okay? So I include every single new term. Okay? Now, if there are additional terms that are the same, so maybe this one had an x there, I put the x in there, right? Eventually I get down to this one. Is that new? No. So I don't put it in again. Does that make sense? Okay. You could put it in, just like back here, we put in an extra 2 here, right? We didn't need it, but we put it in, made the numbers larger. If I put in extra variable factors, it's going to make my quadratic equation that we're going to develop from this equation, it's going to actually turn it into a cubic. Okay? Or if I add too many, it might make it a quartic or a quintic. Okay? So it's going to make that leading power increase. And think about factoring. That's what we're going to do here to solve this. Factoring a quadratic equation is so much easier than factoring a cubic equation, right? So much easier than factoring a quartic equation. So you can, start repeating variable terms, but it's going to make something, it's going to result in an equation that you have a very, very hard time factoring. Okay? Also, something to think about, we don't see it in any of these assignments right now, but if this was like x minus 3 squared, okay, we've already got an x minus 3, right? Okay, but when we choose our denominators, it's this idea here. If I had, 1/2 x plus 2/4 equals 1/18 or something. Okay. Yes, I need a 2, but because of this 4, it's really 2 squared, right? So I need that 2 times 2 instead of just the 2. I need, to get a common denominator, I need the largest exponent of repeating terms. Okay? So if x minus 3 the first, x minus 3 the second, I take the one with the highest power. I take x minus 3 to the second. Is that okay with everybody? All right. Those are things, like I said, you're not seeing those types of questions in your homework tonight or in that assignment, but down the road, that will become something that we want to deal with. Okay? So what I'm going to do, now, you would probably not write this every single time you do one of these problems, but I'm going to go through and I'm going to rewrite each one of these terms with that common denominator. Okay. Now on the right hand side, it's kind of trivial, maybe or maybe I don't know, kind of silly to put x times x minus 3 on the bottom of the 0, right? Whatever that number turns out to be, 0 divided by it is going to be 0, right? So even though I don't write that x times x minus 3 over there, it is over there. So if this was like a 5, you would want to write the x times x minus 3 on the bottom. Okay. But now we look at that denominator compared to that. What did I multiply this denominator by to make it grow into that one? X minus 3. So I got to multiply top by that. So we have 14 times x minus 3. Then you go to the next one. So, okay, this x minus 3, what did I multiply that denominator by to get to go to this one? X. So I multiply the numerator by x. Okay. And then I come here, this denominator is 1. So to make that 1 grow to x times x minus 3, I multiply by x times x minus 3. Okay. Now here's what I hope you guys realize. Just going to highlight it here. What's that a factor? What's x minus 3 divided by x minus 3? That's just 1, right? What's x divided by x? Just 1. What's x times x minus 3 divided by x times x minus 3? Just 1. If I eliminate the things that are yellow, a bunch of factors of 1, right? Do I get back to what I started with? Yeah. So if I multiply that by 1, multiply that by 1, multiply that by 1, multiply that by 1, I still get the same thing I started with, right? It just looks a little bit different. Okay? And that's all we're doing here, just multiplying by convenient values of 1, so we can get all those denominators the same. Okay? Now, just kind of a technique that we can use and a line of logic that we can use. If we start adding these things together, basically what happens is I eventually get, I'm just going to write this, don't write this down, I'm going to get 14x minus 3, I'm not even going to multiply this stuff through yet. That's what you would really get, right? Once you have the denominators that are all the same, you can simply add the numerator. Okay? And put them all over that same denominator, right? Well, understand that if this is a fraction and that's a fraction and they have the same denominator, is this something like saying if I have, let's go, let's go 11 thirds is equal to x over 3. Okay? Same denominators, right? So what's it tell me the numerators have to be? Have to be the same, right? X has to be 11. So if these are the same denominators, what's that tell me about those numerators? They both have to be the same. I have to be able to take 14x minus, what's that, 52? 42? Minus 42 minus 13x plus, that's going to be x squared minus 3x times 2, so 2x squared minus 6x equals 0. Does that make sense? Okay. Now I can combine like terms, so I get positive 2x squared. Done with that. 14 minus 13 minus 6, so minus 5x. Minus 42 equals 0. Is that doable? Now let's see that point, which is like a question 1 through 3, right? Probably going to use quadratic formula there. Maybe. I don't think you have to. Is that negative 84? Two numbers that multiply together give me 84, and that gives me negative 5. 84 divided by 12 is 7. 12 and 7. Negative 12, positive 7. So then I go 2x squared. I'm going to go minus 12x plus 7x minus 42 equals 0, right? So these two terms are exactly the same as that one there when I expand them. Group the first two, group the last two. Factor 2x out, so it gives me what, x minus 6. Factor the 7 out, x minus 6. So I get 2x plus 7 and x minus 6 to be 0. X equals 6 and negative 7. Okay? Now, most of the time, we went through all that work, right? Okay? There's a lot of writing here. A lot of people are going to kind of supplement that work and maybe not write it. This is what I always do. And that long way of doing it is the justification for why this works. But generally speaking, I just figure out what my common denominator is, my LCD, and maybe I just write it to the side here. Okay? Or what I think a lot of people, just so they don't make mistakes, what they like to do is they say, I'm going to multiply this thing by my LCD. Multiply that middle term by my LCD. Multiply this one by my LCD. Multiply the last term by my LCD. And what happens, if we do that, notice at this stage, it's going to be kind of silly that we go back this way, but at this stage here, we start canceling things out, right? I had x times x minus 3, excuse me, and the x's basically cancel each other out and left me with 14 times x minus 3, right? So when I go and have it looking like that, again, the x's cancel out, and these are just 14 times x minus 3. Here, those cancel out, leaving me 13x. Nothing cancels out here, so 2x, x minus 3. And then that product gives me 0. And that's exactly the same thing we had once we realized our denominators were the same, so we can work with our numerators, right? Yeah. But the reason we can do that is there's a lot of, algebra ideas or concepts that we kind of glaze over by doing it, right? But it's simply that we found that technique finds a common denominator for us. When those common denominators are all the same, we can simply do the addition with the numerators. We do the addition with the numerators. Basically, remember, this means that we have x times x minus 3 here, x times x minus 3 there. So we know that we do the addition with the numerators. The denominators are the same, so we really don't even care about looking at the denominators, and we can just set the numerators equal to each other. So there's a lot of hidden stuff inside there. Going the long way, that long route tells us why we can just jump straight to that. Is that okay with everybody? The only thing you want to be careful with when you have rational equations, let's say I go through this problem and I get x to be 3. Can I use 3 as a solution? Will 3, because remember, solutions are things that satisfy this original equation, right? Can you take 14 divided by 3? Is that okay? Can you take 13 divided by 0? Can't divide by 0, right? Okay. So if I were to get a number that spits back to me, that when I plug it in here I get 0 in the bottom, that number would ultimately be an invalid solution. Okay? It does not belong to what we call the domain of that equation, okay, or that graph there on the left-hand side. All right, so the two values. When I look at this problem and start working through it, initially I think there are two, out of all the numbers that exist, there are two numbers that I know are not fair game for this problem. X cannot be 0 and X cannot be 3. Because when I plug those numbers in, I get issues somewhere in that that equation. Does that make sense? All right. And that's always something to think about when you start a problem and when you finish a problem, especially when there are fractions, is when I substitute back in, do I get division by 0? That's going to be one of the number one properties that we want to make sure we do not violate throughout the rest of the year. Okay. Is that question, does that help now? So one of the other ones, I think it's question 5, very similar. It says find all real solutions of that thing, okay? When you have fractions inside fractions inside fractions inside fractions, what do we usually call those? Compound fractions, okay? When you have 2 or 3 words together to make one word, like bookshelf, it's called a compound word, right? When we have multiple fractions make up one fraction, we call it a compound fraction. Now, the more compound it gets, eventually we start calling them complex fractions, because they're kind of complex, right? This would probably be considered a complex fraction. But we approach it just like we normally would anything else. If you had, in that last problem, then we try to multiply everything by common denominator. Okay? So when I look at this, when you look at compound fractions or complex fractions, that is the fraction, that's the division that kind of overrides all other division. That's kind of the governing division of the problem. Okay? So let's just look at this as a numerator and that as a denominator, right? Don't even care that inside the denominator I've got more numerators and more denominators. Okay? What can I do to get this here, this denominator, moved to the other side? Can I multiply by it? If I had 2 over x equals 3 halves, so I multiply both sides by x and get 2 is equal to 3 halves x. Does that work? So why can't we do the same thing here? It's just a little bit of an uglier expression down here on the bottom, but the algebra is the same. So we're going to multiply this side by 4 minus 1 over x, and that's going to cancel and cancel. And I come over here, multiply by 4 minus 1 over x. Now when I do that, I get 2 plus 3 over x. Okay, because this denominator canceled over here, right? Basically multiplying by essentially a reciprocal here. Over here then, that gives me, you can rewrite it this way, or you can distribute. I'm going to distribute, and you see the nice things that happen here. X times 4 is 4x. What's that going to give me? Negative 1, right? Negative x over x. Just find the negative 1. Does that that equation now look like the last problem kind of? Okay, so a lot of times when problems are different or they're presented to you differently, we want to see if we can transpose them a little bit to where they look like something we've done worked with prior. Okay? So this question looks like the last one now. The denominator is a lot simpler than the last one. What's the common denominator for everything here? X, right? So can I multiply everything by x? Multiply that by x, multiply that by x, multiply that by x, multiply that by x, right? That's going to give me 2x plus 3 equals 4x squared minus x. Okay? Some people in the last class, they wanted to move the 2 over first. Can I do that? Or move the 1 over first. Can I do that? Yeah, nothing wrong with that. Okay? Because the next step I'm going to do here is either move the 2x over or move the 1x over, right? I'm going to move the 2x over. And I'll move the 3 over. I get 4x squared minus 3x minus 3. Now when we do this one, okay, we look for a GCF, greatest common factor, between 4, 3, and 3, and there isn't one, so we can't do that. We maybe try the A times C method, so I get negative 12. And I think about numbers that multiply together give me negative 12, but that give me negative 3. So I got 1 and 12, 2 and 6, 4 and 3. And none of those, my alternate pluses and minuses, will give me negative 3. So none of my techniques for factoring work, so what do I always go to? Quadratic formula. Okay. Somebody in the last class asked, can't I always use a quadratic formula? Yes, on a something squared, you can always do that. And my hope is that we realize that sometimes the quadratic formula is more cumbersome than the shortcuts. Okay? But if you want to say, I'm always going to default down to this thing, go ahead and do it. It's a 9, not 16. B squared minus 4a c all over 2a, which is 8. 3 plus or minus 9 minus, so what's that, what? 48. 9 minus negative 48. 57. Over 8, is that right? Okay. Now they ask, I think they force you to type that in as 2 solutions, right? They type in 3 plus radical 7 over 8, comma 3 minus radical 7 over 8. Something that I've seen, and the example from last class actually did this. So I want to make sure that we kind of talk about this. The last class I got just the numbers that showed up. I think it was a 4 plus or minus like 57 over 8 or something like that. I think they're different. No, I think they were 6s and 2s or something like that. What I want you guys to realize is that there is some cancellation that can happen between that 4 and the 8, right? But is there any cancellation that can happen between that 1 and the 8? No. You get a lot of people who just want to cancel the 4 and the 8 and make it, 1 plus or minus radical 57 over 2. You can't do that. And here's the reason. When I have a sum divided by one denominator, that sum is 4. And we can break that apart that way. Right? It's kind of the reverse way of working with common denominators, right? Usually we develop a common denominator so we put numerators together. Here we've already got the common denominators. Let's pull the numerators apart. So now we see the 4 and the 8 cancel, right? That gives me 1/2. But over here I still get radical 57 over 8 because that 1 and that 8 don't cancel. So you can't cancel, but you got to separate them to do that, right? Okay. Because what I get a lot is people to do this. They want to write that this is incorrect. Right? That's not equal. They do this. 4 divided by 8 gives me the 1 plus or minus radical 57 all over 2, and they cancel that. But now if I realize that that's a common denominator, I can split the numerators. I get 1/2 plus or minus radical 57 over 2, and that there is not the same as that there, which we knew this was the right answer, right? Because those two things are different. It tells me I really can't just cancel those two and be done with it. Okay? That seems to be an issue that I get a lot with students in regards to canceling sums like this. Now, if I had 4 plus or minus 8 radical 2 all over 4, now can I cancel here and there? Because they both have a factor of 4 in them, right? Can I cancel this too? Anything under the radical, if it's simplified, it's locked underneath it. You can't cancel. Okay. Remember that radical is a symbol for another number, and that 2 doesn't have a perfect square inside it that can cancel this 4. Okay. So don't cancel radicals. Just cancel the constants or the coefficients outside this. Okay. Obviously, that's a constant. We call that a constant too, but some people like to maybe visualize it as a coefficient because that radical even a treat kind of like a variable. Should probably just call it constant. Does that help on those two? All right. I think what happens a lot of times in this course, especially future courses, is not so much I don't know what to do or you don't know what to do. It's that you go through the process and then you've got varying ways of being able to display your answer. And, you know, for instance, in that last one, you might have accidentally done a step where you think was okay, but it's really not okay. I always go back to my calculator. If I think there's an algebra step that I'm worried about, whether I'm allowed to do it or not, I'm going to violate a rule or not, if I try to type it in on my calculator, maybe... Okay, so maybe we think like this was legitimately okay to do. Well, I know that my goal is to say that this thing, I'm just trying to simplify this thing to that, right? So shouldn't I be able to type this in on my calculator and hit enter and it give me a decimal? Okay, put this all in parentheses up top, all that kind of stuff. But then shouldn't I be able to type this thing in as well and hit enter? And if they give me 2 different numbers back, does it tell me that I've broken a law somewhere? Yeah. If they give me the same number back, then yeah, it tells me I could have canceled that way. All right? So you've got that technology. Try to use it to benefit yourself instead of being, you know, I tell my geometry students that they use it as a crutch because they just let it do all the work for them and they really don't know what it's doing. If you understand how it works, understand your overall operations, that kind of stuff, you can use it as a tool instead of a crutch. So those were 4 and 5. This one here, to solve the equation graphically, okay? Let's just use our TI-83s real quick, show you how to do this. There is a video under one of the lessons that we've done, I forget which one it was, that walks you through this. We can do it together. My computer's being weird today, where it won't put like new windows that open up. It's hiding them behind all the other windows that are already open. I think I just gotta restart it, but I don't have time to. So we're going x cubed. That's the way you want to do it. You're going to go to the y equals. And you type in x cubed minus 7x squared minus 5x plus 35, and just leave that as y1. Okay? There's 2 approaches that you can use here. Okay? Because remember last week we talked about how the left-hand side of your equation is a graph and the right-hand side of your equation is a graph, right? Well, if your right-hand side is 0 the graph of y equals 0 is what? The x-axis. Okay? So, whenever I see y equals 0 over here, I don't write that down here. Okay? Because I know that I've got a better tool in my calculator to find me intersections of the x-axis instead of the intersection of this equation and then a second equation. Okay? So I'm just going to leave that as y1. I'm going to go to graph and just see what my graph looks like now. Looking at this, I don't get the entire cubic. Okay, it's going to kind of look like an inverted S. But I don't really care as long as I have the 3 intersection points that we're looking for. Okay, so as long as I have that intersection point, that one, and that one showing up, and it's a cubic, so I know I should have 3. If I have that, I don't need to see the maximum minimum. Does that make sense? Okay. So we don't need to adjust the window or anything like that. We're going to go straight to the second and calc key, okay, which is actually the trace key, but it takes you to the blue stuff. You all know that when I hit the second key, it starts using the functions that are written blue and above it, right? Okay. Now I'm going to go down to, last week we did intersect, okay, but now because I'm looking at the x-axis, where we cross the x-axis, I'm looking for what option up there? 0, okay? Zeros, roots, x-intercepts, they're all synonyms. So I'll hit 2, okay? Now, what it's going to ask me, kind of think about the theory here. It's going to move my cursor. You couldn't see my cursor initially because it was off the screen, but if I look at the x values, I know where it's kind of at, and I know that this x value here is around -2, right? So I see my cursor's at like -7, keep moving it, and then it finally shows up. Does that make sense? So if you don't see your cursor right away, it's because it's being hidden somewhere else on the graph, outside the viewing window. You just got to move it around to where you see it. Okay. Now, you see where it says left bound here at the bottom left. Okay? They're basically asking you, move your cursor to where it's to the left side of where you think your x-intercept is. Okay? Well, I think my x-intercept is right there where the yellow is that now to the left of that? My cursor's now to the left of that, right? Does that make sense, everybody? So now I hit enter, and now it asks for a right bound. So I'm going to go and move my cursor to where I think is to the right of that x-intercept. Okay? So what we have just done is we have used a theorem that's called the intermediate value theorem. Okay? When we clicked here on the left-hand side, it would have given me a y value of what? What kind of number would the y value down here be? Negative, right? When I clicked on the right bound, it would have given me a y value of positive, right? Well, I just developed now a region in which I have some y values that are negative and some y values that are positive. And if I travel from the red to the blue, what number do I have to pass in between? 0. So I told my calculator, look at all these red values, look at all those blue values, and at some point you're going to transition between a negative to a positive, so you had to pass 0, right? And that's the y value that we're interested in, and we're going to ask it, can you find then the x value that's associated with that? Hit enter again, and it gives me my 0 to be negative 2.24. Okay? And we'll round those to the nearest hundredths place. Okay? The next thing we're going to do is go second calc again and just repeat the process on the other zeros. So I'm going to move my cursor to where it's to the left. Come on. I still see my x values at like 0.6 here, so moving it. Should show up here pretty soon. There it is. Okay. I see at this, I'm guessing it's a little bit bigger than 2 there, and I was seeing this number here to be like 0.6, so I knew it was still up there off the screen. So move it to the left bound, so that looks like it's to the left of the x-intercept, or move it to the right, So I've just said, now I'm going to transition from a positive number to a negative number. So again, I'm going to pass through 0 to do that. And I get 2.23. And I can do it one more time to find that next one. Does that make sense to everybody? Okay. Something you could do, let's say this equation, here it's saying is equal to 0, right? Well, what if it said equals to 3? Could I move that 3 over and make it a 0? Yeah. Or I could do this. I could go to y equals and do 3, and now graph that. And now basically I'd go to the intersection tool, and I'd look for that intersection, and that intersection. But those x values are going to be the same thing as if I moved everything down 3 units by subtracting 3 to both sides. And then using the 0 tool. I seriously think that this calculator, like we could legitimately do like a semester course on how to use your calculator. Maybe even longer. So there are going to be some things that we talk about that we kind of glaze over, but hopefully if you didn't catch that, you go home, you watch the video, and you can learn that process. It's going to be very helpful for a lot of things that we do later on to be able to do that. Seven. Number 8, before we do 7, let's just talk about 8 and watch the video. I did this one in the last class, so we're kind of running out of time here. So I want you to watch that video to do number 8. But it says use complete the square, right? Does the program ever know that you've completed the square? That's the technique that you use. We've got 5 different techniques to use. And it tells you to use one. If you don't like that one, you don't feel comfortable with that one, does it know if you used a different one? No, I'm not asking you to show your work, right? Hopefully we are doing work somewhere. But I don't care. Don't complete the square here. Use quadratic formula. That'd be so much easier, right? Be cautious though. Here's something I would do. Is there a common factor that you can take out of all 3 of those terms there? Or ultimately all 4 of those terms? Take a 2 out, right? So make that right on this. Make that 2x squared minus 8x plus 7 equals 0. Okay, factor that 2 out. Now, here's something to be cautious of, and I talked about this in the last class. We really factored out that way, right? That 2x squared plus minus 8x plus 7 is representing just a what? When I know what x is, what's all that condense down to? Just a number, right? Okay. You got 2 times just a number, okay, is equal to 0. So maybe this is just x, okay? Or if I have 2x equals 0, can I divide both sides by 2 and get x equals 0? Does that make sense? So the idea here, we factored the 2 out, but that we're going to then divide by 2, come over here, divide by 2, so we're left with just 2x squared minus 8x plus 7 is equal to 0. Okay. People get confused on when we factor, when can that GCF disappear, and when does it have to stay. If I had this, okay, just an expression, no longer an equation, right? When I factor GCF out, that factor of 2 has to stay now. Because there's no division here now, right? There's no division of both sides by 2. It has to stay, because when I have an expression, and I simplify or rewrite that expression, this expression needs to say exactly the same thing I started with, right? If I get rid of that 2, they no longer say the exact same thing. With an equation, we can divide both sides by that factor 2 and go away. Okay. Does that make sense? All right. Then I would use, with that 2x squared minus 8x plus 7, I'd use my quadratic formula. Okay? The reason I took the 2 out is because it's going to make my numbers half as big as they were here when I'm inside my quadratic formula. Okay. Last class we had the debate whether if you're on a test, because tests are usually generally going. If you're in a math course and there's 3 or 4 different ways of doing something, a lot of times they say question A, do it this way. Question B, do the same problem using this technique. Okay? And you want to abide by those things. But if I just give you a question that says complete the square on this, you can use the quadratic formula. Because didn't we talk about how the quadratic formula is the same exact process between the squares? Okay? We took ax squared plus bx plus c equals 0, completed the square with it, we got the quadratic formula. So I view them as synonyms. Okay? Doing the same things. I don't really care. My whole goal, hopefully your whole goal, be able to arrive at a solution and know why you were able to arrive at that solution and know when that technique is applicable and why it made sense to you to use it. Is that okay with everybody? All right. So you can finish that one just like questions 1, 2, and 3. Number 7. I'll help you set this up. An object dropped. So just if I stand on top of the chair and I drop an object, okay, that object's going straight down, right? Okay. The idea though is that over time, its height is still going to be modeled against the time axis. Its height is still going to be parabolic. Okay. So suppose an object is dropped from a height h sub-0 above the ground, then its height after t seconds is provided by that formula. Okay, negative 16t squared plus h sub-0. Remember, the formula we talked about so far in class was negative 16t squared plus v sub naught t, right? Initial velocity. So the idea is that we are standing, if I stand on my, I don't even have to stand on my chair, but if I'm here and just drop it, there's no velocity there, right? No initial velocity, okay? So that's why there's no v sub naught there. Okay? It's just that initial height, okay? Throw it, if I throw it, now I've got a velocity behind it, right? Okay? So then there would be that v sub naught in that initial height, okay? So here, we're going to go h equals negative 16t squared plus the initial height, and they say 93 feet, right? Normally, if a velocity, there'd be a t on there, because that's that, the v sub naught times t is that velocity component. This is just the height, okay? So now it says how long will it take to fall half the distance to ground level, okay? Well, ground level would be half the distance would be 93 over 2, right? Okay, so I put that as 93 over 2, and I use my quadratic formula to solve for t. Okay. How long will it take to fall to the ground? I let h be 0, and I solve that. Okay. It might actually be easier to answer the first question. It might be easier to answer this question first. Find out how long it takes to hit the ground, and then if I take that answer and divide it by 2, won't that put me where it froze halfway in between where I let it go and where it hits the ground? Take that number, divide it by 2, you get that number. Okay, so might make sense. Can you answer them that way? Does it force you go that one and then that one? I guess it does. That's my fault. Because, yeah, you're right. Because the acceleration due to gravity is changing per second. You're right. My fault. So what's that? Gives you like 3.4, right? So you have to put this as 93 over 2, and then 0. Sorry. Is it okay? All right. We have time. Man. That's not due till tomorrow.